The graphs of y equals the derivative of g equals ax squared plus bx plus c, and h of x equals 2x minus 4 are sketched. The graph of y equals g prime of x is the derivative of the cubic function g. The graph h and g prime have a common y-intercept at E. C and D are the intercepts of the graph G prime. A is the intercept of H, and B is the turning point of G prime, and AB is parallel to the x-axis. Lots of words, but they want you just to make sure that you do understand what is happening. This is the derivative of a function g that we don't know. We know it's a cubic graph that's going to turn. There's my line and there's an intercept. Okay. First question. Write down the coordinates of E. E is that point. If I look at E very carefully, E lies on the parabola but also on the line. I have nothing about this one, but I do have information of that one, because h of x equals 2x minus 4. Can you tell me what's the coordinates of E? Obviously, E is the y-intercept, so E will have the coordinates 0 and minus 4. That's the C value that I see there that I can bring in there. The C value of the line. My second question. Determine the equation of the graph of G prime in the form y equals ax squared plus bx plus c. So this time around, I'm zooming in on that parabola, and I need to see what information do I have. Oh, I have a root there, and I also have a root here. So I have two roots. And to find the equation of the parabola, old news. I can find that parabola by saying it is y, that's 9.2, equals a in x minus my one root on the screen, minus 2, so it becomes plus 2, times x minus the other root, that is 6, so it becomes minus 6. What I need to do now is just multiply out, and I keep a in front. X squared plus 2x minus 6x gives me minus 4x minus 12. Not done yet. Ax squared minus 4ax minus 12a. I can't do anything further here, so I'm going to go look for a point on the graph that I can substitute. And the only point I have is point E, is also on that parabola. And if you look back at my calculation on my page, then E had the coordinates x is 0, then y is minus 4. So x is 0, 0 times a is 0, 0 times 4a is another 0, so then minus 12a will be equal to minus 4. And A must be equal to minus 4 divided by minus 12, which will give me 1/3. And this value I throw back in there. And Y becomes 1/3 x squared minus 4 times 1/3. X minus 12 times 1/3. I'm writing it out so that people can follow what I'm doing. And that gives me 1/3 x squared, and that is minus 4 over 3x, and that will give me nothing else but 4. And there I have the equation of my graph. Please note, you can verify immediately if your answer is correct, because this minus 4 must correspond with that minus 4. So I'm back where I started off originally. So, this time around they're asking me, write down the x coordinates of the turning points. Keeping in mind that we know at the turning points, the derivative is equal to naught. So let's look at my sketch. The derivative, this is my derivative. So where's my derivative naught? At that point. So what's the x value? I'm sorry, I must go back. I clicked by accident. At that point, my derivative is naught. They want the x coordinate. So I know my one turning point will be at x equals minus 2. And you know where's the other one, hey? The other one is at that point. Because that's the other point where the derivative is naught. And at that point, it means at x equals 6. Easy. All you need to know is that you need to understand that this is the derivative function. And at the turning point, the derivative equals naught. And for 2 marks, obviously, there must be no calculations at all. Okay, write down the x coordinate of the point of inflection of the graph of G prime, of G. The point of inflection, I hope you can still remember, the second derivative is equal to naught. In other words, this is my derivative. The second derivative is there at the turning point, which is just a normal turning point of a parabola, which means I know the turning point is midway between my 2 roots. So, I can do that fairly easy, because all I need to say at 9.4 is to say my 1 root, the distance between this point and that point is 8. You agree with me? That is 2 units, and that is 6 units. So altogether, I have 8 units there. So it will be 8 divided by 2, which gives me 4 units. So the x value must be there at 4. So this value here, b's value here, must be at 4. If you want to, you can also work out the second derivative. Right? Your answer must still be 4. And the last question, they ask you a fairly tricky question. Explain why G has a local maximum at this point at x equals 2. So let's see. Let's see, how do we do that? So if we look at that question, then we'll see that if I look, remember this is the derivative. So if I come closer here, what would you say, what is the value of the derivative here? Oh, the y value is positive, it is positive, and is positive. Derivative means the gradient. And if the gradient is positive, the gradient will go up. The gradient is positive. It will look like that. At C, at that point, the gradient is 0. The derivative is 0. The gradient looks like that. No gradient at all. And if I come below the line, then you'll notice that my gradient is negative there. So therefore, a negative gradient comes down. And from this simple little sketch that I did here, I can show you that a turning point like that can only be a maximum turning point. How do we say this so that the examiner can understand it? I did a little picture so that you can see it, but you need to write it in such a way that the examiner can understand it. And exactly how we did it. We said, for all values, if x is less than minus 2, the gradient was positive. Simple. At x equals minus 2, f prime of x was equal to 0. And at x greater than minus 2, the derivative or the gradient was, or rather I should say, equal to negative. It was less than 0. Please note, I'm writing it in different ways. I first wrote it in words. I wrote the gradient and derivative means the same thing. The f prime of x equals 0, f prime of x is less than 0. And if this is the situation, then this implies that it must be a maximum, a local maximum turning point. Now, as you can see, what we did here was we did not once give you the original graph. But from the derivative, I can have a fairly good idea what that graph and where my turning points will be. I did not manage to get to example 2 because I thought because this problem was so much different, I felt it was important for us to have a look at this particular graph.